Thank you very much for the introduction. I'm Steve Ertel. I work with the LBTI team, Large Binocular Telescope Interferometer team. I am an instrument scientist there, and about a year and a half ago, I've taken over the team lead. I'm mostly working on the operations and science side with the instrument, so I'm not really too much an instrumentation person. However, I'm backed up by an amazing team of scientists, other scientists, and also engineers, of course, who really take care of this for me, and we work together to make the whole instrument work. I am somewhat free to speak about the LBTI because I'm not the genius who envisioned and built it. That's Phil Hinz down here, who was our original PI and just recently moved over to the University of Santa Cruz for a different job. So that's why I'm taking over the team. So yeah, I'm going to talk about our instrument, and I have the pleasure to introduce you to it after we've heard quite a bit about it already in the past talks, and we'll hear more in the next days. So I'm going to mostly go over a little tour of our instrument, actually, and of the LBT as a whole. So the LBT is the Large Binocular Telescope. It is an international consortium with partners in the US, in Italy, and in Germany mostly. Plus a few other partners around the world who are contributing smaller things. The LBTI is the Large Binocular Telescope Interferometer. The I is not all that critical in some cases because most of the science that we're doing is actually related to infrared imaging, which is a more productive mode for us, while the interferometry is, of course, the most exciting thing and the thing why the instrument is built. Generally, I'm really excited to work at the LBTI because it's really the whole instrument, and to some part, even the telescope itself has been designed for that specific task, or at least with this task in mind. And it's really designed for doing exactly the science that I'm doing. So that's really great to be there. The whole thing is located on Mount Graham, which is here in the southwestern United States. It's at an elevation of 3,300 meters, so that actually looks weird here for many people. There's trees around it. That's because even at 3,000 meters elevation in summer, it gets reasonably warm up there, and that's actually one of the regions where it rains in Arizona. But that's actually quite important together with the location of the LBT. It's, as far as I know, the only 8-meter telescope that is located in continental climate, which means that in winter it gets really cold up there, about 10 degrees colder than Paranal typically in winter gets, which of course helps with infrared astronomy. If you have a question why I painted Arizona blue so close to November, I'm happy to explain it to you after the talk. So that's the LBT, that's our beautiful telescope. It has those 2 mirrors in one dome. And the whole idea, if I zoom in here, is what you can see is those two 8.4 meter mirrors. They're really huge. They are located on a common mount. So they are always pointing in the same direction, and they're located in that one plane that always points in the same direction. And I mentioned already those 8.4 meter mirrors, and we've already heard before that they're separated center to center by 14.4 meters and edge to edge by 22.7. So we typically say 23 meters. Which gives the LBT its superior resolving power compared to most other telescopes, definitely compared to all non-interferometric optical and infrared telescopes. The LBTI itself is located in the middle here and also on the mount, so it also moves with the whole telescope, and it combines the light, so it gets the light from the 2 mirrors and combines them on one science camera. So both mirrors always send the light to the same science camera if we're using both. So the LBTI itself is a strategic or PI instrument developed by our team at Stewart Observatory with contributions from other partners, of course. It is designed for very sensitive and in particular high contrast and high angular resolution observations in the thermal infrared, mostly in the LM and N band. We can also do JHK, but I'm not going to go into too much detail on that in this talk, of course. So it does adaptive optics imaging with the 2 mirrors. It does nulling interferometry. It does Fizeau or imaging interferometry. We do aperture masking with individual mirrors or phased, as Steph Salem has shown a few, like an hour and a half ago, for the phased 2 mirrors together. And we're also using integral field spectroscopy. And as I mentioned already, the LBTI is really designed to exploit the full resolving power of the LBT. LBT, which is this up to 23-meter telescope. The whole thing has been funded by the Exoplanet Exploration Program from NASA, together with contributions from the NSF, from the LBT Corporation, and other smaller partners. And its core mission, and that's why NASA funded the LBTI in the first place, is the host survey for exozodiacal dust. And I'll talk about this a little later after I'm through with the instrument itself. So here's a little scheme of the optical path of the telescope, of the LBT. Of course, the light comes from the sky onto the primary mirrors. As I mentioned, they are in a common plane on a common mount, which always points in the same direction for the two. Then the light goes up to the adaptive secondaries, and we're going to do this tour pretty much down the optical path, and we start with the first stop at the adaptive secondary mirrors. So that's actually has been described already for other instruments in previous talks, a very important component of very sensitive thermal infrared observations, because you have this warm surface, which is the secondary mirror anyway, and you can use it for adaptive optics correction if you have a deformable mirror there, which saves you the multitude of additional optical surfaces that are typically warm if you do the adaptive optics in addition on a small deformable mirror in the instrument or near the instrument, like NACO, for example, did. So the adaptive secondary can correct up to 600 modes and up to 1700 hertz, so 1.7 kilohertz. So that's actually very close to what people call extreme adaptive optics. So the LBTI, if we go further downstream, so there's first the tertiary mirror, which is not particularly remarkable compared to other tertiary mirrors at, for example, the VLT. And then we enter our LBTI instrument here in the middle, which is about to scale on this picture, and I'm going to zoom in a little bit. So you see how the light's coming in from the two sides here, and then enters our instrument. And here's another thing that I want to point out. I've already said this a little bit. So the instrument is located together with the mirrors on the same mount. So it always is oriented the same way with the pointing direction of the telescope. That's actually very interesting if you think about the talk that Olivier Absil has given yesterday, where he emphasized the importance of pupil tracking during infrared observations to reduce the background variation in particular. So the LBTI can't actually do anything else. The LBTI doesn't have any derotator. We always do pupil tracking. So to give you a little more scale, here's a couple of our team members in front of our instrument. So the whole thing is about 3.5 meters high and about 5 or 6 meters wide. And here's a little more of what you're supposed to look in that picture. So we have, again, the light from the two sides, and we have this structure in the middle here, which is our beam combiner, which actually gets light from the two sides. And then we have our imaging camera down here, which really has all the detectors. And that's a little bit of a scheme again. So that's the beam combiner, light comes in here, gets a couple of reflections here, goes down to our science cameras. So a little simpler to get started with the along the optical path. Again, here's our beam combiner, which has a temperature of about 90 Kelvin typically, and is used for beam steering and path length correction for interferometry if we do that. And then down here we have our nulling and imaging cryostat, or NIC, which has a temperature of about 60 Kelvin and hosts our science cameras and the phase sensor for the interferometry. But before we actually get to our science instruments, there's this part up here, which is our adaptive optics wavefront sensors, which are, of course, a very important component of the instrument. So Bernhard, or actually yesterday morning, talked about very large, so extremely large telescopes and mid-infrared instrumentation there. And he actually mentioned that they are planning for Metis to build the wavefront sensor unit into the cryostat, which I think is, of course, challenging, because everything that's in the cryostat is, for any intervention, always a full cryocycle away, which is typically a couple of days. So that's challenging. But of course, you want to remove the one warm optical surface that he mentioned, which is the wavefront sensor dichroic. So the LBTI is not having a wavefront sensor dichroic itself. What we're doing here on the right is we just use our entrance window itself as the wavefront sensor dichroic as well. So the light enters, the infrared light enters our instrument, our cryostat, and the visible light is reflected off of this and down here into the wavefront sensor. Now for the LBTI itself, for our standard observations, we would only need one dichroic because we're always using the same one. So that whole thing wouldn't even have to move. However, for different other projects that I'm not going to mention, but they're also related to the LBTI and using part of our beam combiner, we do want to have this movable so we can put different dichroics in. And that whole thing here is able to rotate. So it's on a hydrostatic bearing, which means it holds the vacuum, but can also move and put different dichroics into position. Right now, there's only our dichroic mounted here in this picture. And then, so this dichroic up here sends the light from here down to the wavefront sensor board, which is down here. And I'm not going to go into too much detail, but the important point here to know is that it's hosting a pyramid wavefront sensor, which has recently been upgraded to an OCAM detector. And we actually correct, or we are able to close our adaptive optics loop on stars or even extended objects altogether as faint as an R magnitude of about 18, which is amazing. It pretty much makes lasers almost obsolete. So if we go further down the optical path, the infrared light goes into our instrument, is reflected off an ellipse mirror here, which has actually optical power that creates a pupil plane up here on this mirror, which is nicely named our pupil mirror assembly on both sides. So that's our path length correctors. So we call them fast path length correctors because they are shown down here. They're mounted on a tripod of piezo devices, so piezo stacks, which allow those mirrors to move in piston, tip, and tilt. So they are used for our piston correction for interferometry, generally for our tip tilt correction. And recently, we've also implemented using them for fast chopping and for chronograph centering. And those move at a kilohertz frequency. So on the right side, this is actually mounted even on a translation stage, which does our optical path minimization between the two mirrors before we use them to correct optical path delays for the atmosphere. So one thing of those pupil mirrors that's interesting to point out is this dark mask in the middle. So since they're located in the pupil plane, we use this as a cold stop to block the central obscuration of the telescope, which normally would add significant infrared light. And then the light goes up to some roof mirrors here. We call them roof mirrors because of their shape and because they're located on the roof of the instrument. And then the light goes down into our imaging camera. So that's Nick, our cryostat, shown for scale with I don't know who that is, but one of our engineers on the side with his hands. So you can see how small this actually is. It's about double the size because under this level, there's another level of about the same size. So altogether, it's about twice the volume. And most of it is empty right now because that's when it has been assembled. But just to show it for scale. So down in this cryostat, we have our two science cameras. So we have the light coming in here. Then there's a trichroic actually here that sends the 3 to 5 micron light down to our short wavelength camera, which is called LMIRCam. And that's a LMIRCam camera, which can also image the JHK light if you put a different dichroic in here. And it's used for imaging 23 meter Fizeau imaging interferometry and AGPM and APP coronagraphy, aperture masking. And aperture masking either individual aperture or for 23 meter aperture. It has an H2RG, so 2K by 2K pixel detector with a 20 by 20 arcsecond field of view and 11 milli-arcsecond pixels, which are undersampling the single telescope PSF because we also want to use those for interferometry, so we need to see fringes. And it's running on a Macy card and a sidecar controller from Teledyne. So what I'm showing down here are some code stops as we're imaging the light from both telescopes. Typically, everything has, or almost everything has to be double. So those are two code stops for each side one. And in the middle here, we have another code stop for the central obscuration and for the swing arm that holds the adaptive secondary, actually. On the right side, there are our vector APP chronographs, which are just another nice picture and also are dual as pretty much everything. Then we have our then we have AILS, which is the Arizona Landsat for exoplanet spectroscopy. And that's pretty much an optical assembly in LMIRCam, which is used for integral field spectroscopy. So it's a set of magnifiers, prisms, a Landsat array, and it has a 2 by 2 arcsecond field of view. So because we need to magnify the field of view onto our LMIRCam detector. So it's actually, this is important to point out, it's the world's only thermal infrared IFU that currently exists. Then we have our second science camera, which is called NOMIC. It's our N-band camera, which is also used for imaging, nulling, and Fizeau interferometry. And also, yeah, that's pretty much it. It has an Aquarius detector, very similar to Vizier or NEAR, if you want to call it that way. It has an 18 by 18 arc second field of view and 18 milliarc seconds per pixel. It's run on a Sophia Forecast Electronics, and we're actually exploring an upgrade to a 13 micron H1RG detector that we have at hand, and that's led by Channel Licensing. Finally, we have our FaceCam, which is our face tracking camera, which is operating in H and K band. And it's used for interferometric tip, tilt, and piston sensing. It's currently running on a picnic detector. We are exploring an upgrade to a Saphira array to run this at a much fainter limiting magnitude, and that's led by Jordan Stone. So FaceCam, why does it have such a relatively bright limiting magnitude? The reason is because we do tip, tilt, and phase at the same time. So we actually disperse the light onto a pseudo pupil plane where we see the fringes here. And then if you do a Fourier transform of those, you can get from the position of those spots in the amplitude, you can get the tip and tilt, and from the phase at the location of those plots, of those spots, you can get the phase of the whole thing. So we're doing actual phase delay tracking, not group delay tracking, compared to many other interferometers in the world. So after I'm gone through all of this, and I'm sorry I had to rush through it a little bit, I want to go into science. And as I mentioned already, the core mission of the LBTI was and still is the HOSTS program, which is the main science driver, and it's designed to search for habitable zone dust around nearby stars. So the goal is to characterize the amount of dust and the distribution of the dust and evaluate the risk for future exo-Earth imaging missions. So this dust creates photon noise for a potential space mission in the future that wants to image habitable planets in the habitable zone. Since this dust is typically located in the habitable zone, it has about room temperature, so N-band is the right place to detect it. And so the LBTI has been funded by NASA to execute the survey and prepare for this for those exo-Earth imaging missions. Because depending on how much dust there is, you either have to build a bigger telescope or you have to live with fewer detections if you want to cope with a larger amount of dust. So recently the survey has been completed. We've observed 38 stars. We have 10 detections, which is a very, very high detection rate. And one thing that we find is that exo-Earth imaging is actually possible. So one thing I want to emphasize here is that this is really a case where mid-infrared imaging from the ground is really used for extremely high precision and sensitivity, which is something that's very rare. So if you compare this to, for example, a space mission like WISE, which has tried to do that photometrically, you're limited by the brightness of the star and the contrast between the disk, and so the dust and the star. So you can only get down to about 1,000 SODIs, and the unit of SODI is the amount of dust in the solar system. So you only reach 1,000 times the sensitivity of what a solar system dust disk around those stars would be. So the other instrument that has done this in the past was the Keck interferometer nuller. So we're using nulling interferometry for that from the ground. And they managed to go down by almost a factor of 10 more sensitive than Keck, than WISE, than space-based observations. However, still not really close to what we would call the SODI, solar system SODI level, around 1 SODI. So then along came the LBTI, and of course, if you do interferometry, you can't observe as many stars as WISE did. But the LBTI pushed us by almost another factor of 10, and you can see for our most sensitive systems, we reach almost down to solar system levels, which is amazing sensitivity and very important to characterize these typical dust disks. And you can see this by our 26% detection rate. So we're actually seeing almost typical systems. So a little bit of science about that. I'll be really fast on that. If you do nulling interferometry, you don't get very much or very nice pictures, but you mostly measure a flux and you can do statistics on those detections. So one of our main results is that there is a strong correlation between systems with cold dusts like Kuiper belt debris disks and this habitable zone dust. So there must be a connection between those two. However, one of the other very exciting results is that we also have the very first detections of stars without this cold dust. So there must be a different origin, or we might not be able to detect those cold dust disks. And we have the first detections around sun-like stars, actually quite a significant number here. which is important because those stars are the main targets, the most likely targets for this exo-Earth imaging mission. So that's very important to look at those. The other thing is that there is no clear age correlation between this dust, the amount of dust and the detection rate and the age of the systems, which is surprising, but also gives important clues into where this dust is coming from and how it's formed. So we're of course doing other science as well. So the HOST survey was one of two very large surveys. The other one is the LEECH survey that has been mentioned in previous talks already, which is a survey for a direct imaging, AO imaging survey for giant planets around mostly mature stars. I'm not going to go into detail about that because we already heard about that. But I'm going to do other stuff. One thing that we've done recently is this image up here, which is an image of a quasar lensed by a foreground galaxy. And Terry Jones, our PI on that, science PI on that project, actually used the flux ratio between those two sources here to constrain the distribution of the dark matter in this foreground galaxy that you can't even see in this image here. So the important thing here was that we were able to close the AO loop on that source itself and get actually decent correction out of that. That's, I think, 13th, 14th magnitude and obviously resolved as well. Other things are VY-CMA that was already mentioned in the previous talk as well, where Mike Gordon was able to, for the first time, image the thermal emission of this ejected clump and thereby constrain the amount and the properties of the dust that's been ejected. So Kevin Wagner already talked about our programs that focus on disk and exoplanet imaging. Another thing that I also want to point out is this observation of WR140. So that's one of the Wolf-Rayet stars we already heard about in previous talks today as well, where we were able to image the temporal evolution of the ejected dust event. So that's something that's also a very nice result. So we're doing this kind of science a lot. A lot of our science that we do are actually people coming up with crazy ideas what we can use the LBTI for, which is one of the reasons why we aren't too productive compared to, for example, a facility instrument at the VLT. We're also an instrumentation experiment, and we are often just demonstrating a capability. We're using it once, we're getting really excited about that, but once we're done, there's already the next exciting thing around the corner. So a lot of the observations that we're doing aren't routine modes, but we just push the capabilities of the instrument for specific science. So again, there has been, this has been mentioned before already, but there's also a similar observation on Betelgeuse that Narzi is showing in his poster. Also, this has been covered by Kevin Wagner's talk already. One of the really exciting things is our ALS integral field unit. So it's the world's first thermal infrared integral field spectrograph, which gets spectral image cubes that can then be analyzed for spectral information and for spatial information. And this can in principle also combined with coronagraphy, which is something we do now routinely, and also with interferometry. What I'm showing here is an example of Io, the Jupiter moon Io, with the Loki patera here, where you can actually resolve that and get spectra all across the surface of this moon, and then get spectral information about the emission. Jordan has a talk about how we use this for exoplanet observations and high contrast imaging. And Eckert already mentioned Fizeau interferometry, and Steph Salem has, thank you. Steph Salem has already shown a different result where we use this for aperture masking. I want to show again Io, which is another nice science demonstration, where we can actually exploit the 23-meter effective aperture of the LBT. At the same time, with Fizeau imaging interferometry, we still get the 20 arcsecond field of view, and it really makes the LBT the first 30-meter class telescope, if you want to say it that way. This also can be combined with aperture masking, as Steph has already shown, and in principle also with integral field spectroscopy and coronagraphy. Because what we're getting here is really just a weird-looking PSF compared to interferometric fringes that you get from optical on baseline interferometry, for example. So down here in the bottom, I'm showing for comparison an image at about 4 micron of Io with the LBTI taken with single aperture, 4.8 meter resolution. And then to the right, the same target observed with 23 meter resolution and image reconstruction. So you can see the amazing structures that you get out of against the background in the higher resolution here, which is really nice. On the right here is a movie that I'm actually going to play. So that's individual observations before reconstructing an image. And you can really see the fringes here, the just weird looking PSF, as I said. There's a whole interferometry lecture in that movie. But what's happening in this movie here is that Europa is moving in front of Io during our observations. So we're actually seeing an occultation of one Jupiter moon by another one. It's a really nice and impressive observation. Again, I think I already pointed that out. So Eckert Spalding is showing a poster and a talk about this mode, and Steph Salem has already shown science results from aperture masking of this mode. One last thing that I want to show is a plot related to what Kevin Wagner has been showing, which is our sensitivity, predicted sensitivity for habitable zone, massive planets around nearby stars. Kevin has argued that we can reach a 2.5 times lower or better sensitivity than the NEAR experiment in same integration time. I actually decided to push this plot a little further, and if we can implement Fizeau imaging for that, we can reach even another factor of 3 in sensitivity, and we can also reach a smaller inner working angle, which according to this parameter space plot here, and this is really just a really quick line drawn in here, so I need to back this up with more computations. But with this, we might actually be able to reach a couple of super Earths if they are there. And again, see the poster by Kevin Wagner on that, at least for single aperture imaging. And with that, I leave you pretty much with the related presentations and some references from my talk. I've already mentioned the presentations. One thing I want to highlight is Eckert Spalding's PhD thesis, which really nicely shows the history of the LBTI and the LBT, and then focuses on the whole Fizeau interferometry part. So that's, if you want to know more about that, that's a really good read. And the LBTI instrument as a whole has been presented most recently by Phil Hinz in his SPIE paper in 2016. So I let you read this from the recording and from the slides as they are shared. But I want to move a little bit further, since there are a lot of friends of my friends in Europe here at this conference, and I got a lot of questions about that. Yes, it's the US, and everybody knows that the virus and the politics really suck these days. But all of this is going to be over at some point, and hopefully actually in 3 weeks, at least in part already. But what's going to be left is the beauty of the US, the west of the US, all of those things, and the nice people. So I want to point out that there are other things than what you hear in the news right now. And with that, I finish my talk. Thank you very much.
Thank you for this nice LBTI overview. I think we have time for 2 questions or so. Can you describe how you get rid of the shopping residuals in N-band using your cryogenic shopper?
So shopping residuals in terms of background are, so variable background, are actually very small. We have just started using this in commissioning observations actually a couple of weeks ago, and Kevin is working on those data. So I'm not able to really characterize this in much detail yet, but we have the data. And so we don't see strong background variations from that. The other thing is to synchronize the chopper with the detector, which is a whole nother challenge that we're still working on.
Then the next question is concerning the AO beam splitter. There's another big advantage to put this inside the cryostat, apart from thermal aspects. NCPAs and vibrations not compensated if the AO WFS is not directly mounted to the instrument. Is this not a problem for the LBTI?
That's definitely true. You've seen, for example, the PSFs by Narsi that he's been showing on when he presented his poster, and you can look at his poster. So there's some significant trefoil in there. So we do have NCPAs. We are able to calibrate those. So for example, the reason why the advantage of not having an instrument derotator is that NCPAs are extremely stable with pointing direction, elevation, and so on. So what we can do is try and calibrate those out and then correct for them on the AO side. And then you pretty much have a not perfect AO shape, but you get a better shape on the instrument. And we've been working on implementing this more routinely, actually also just a couple of weeks ago. So we can correct for that, but it's true that is a problem.
Okay, one last question. Did you try to measure the size of Eos volcano craters using the Europa lunar occultation?
We have not done that, but the occultation actually, and also a lot of other data like the ALS data, allow us to do things like that. Actually, we can just from the Fizeau images, as you can see here, those fringes are blurry compared to this volcano. So what you can see here is that this is actually resolved. So we can measure the size from that directly. Altogether, those observations together with those ALS observations here have actually not only shown that, but also shown where the lava is coming from and in which direction it is flowing on this volcano crater. So there's a lot of work in the literature, and I encourage you to look at Catherine de Clerc's paper here and other related publications recently.